Okay, started.
All right. So, hi everyone. My name is Lin Yu from Xi'an Jiaotong Liverpool University, and I will be the session chair today. So, our session has 6 exciting papers on topic of immersive visualization and visual analytics. And you can post your questions, comments, or insights in Discord or in Slido, and the volunteers will pass these questions to us. Okay. And so each talk will be about 10 minutes long and followed by 2 minute question and answer session. So I will give the presenters a reminder when you reach the 10-minute mark. And you will also need to start wrapping up your presentation when I remind you. So now let's start with the first paper, which will be presented by Tao Lu. Okay, so the title is CompositingVis, Exploring Interaction for Creating Composite Visualizations in Immersive Environments.
Okay, let me share the screen now. Is this the correct view I'm sharing?
No, this is not correct one.
Okay.
No, this is your.
Oh, that's great. Now it works.
Yeah, great.
Okay. All right. So, yeah. Hello, everyone. My name is Tao, a master student at Georgia Tech. I will first also won't be able to attend due to some schedule conflict, so I will be presenting today. And our work is CompositingVis, exploring interactions for creating composite visualizations in immersive environments. With the rapid increase of data volume and complexity, users may need multiple views to analyze their data. For example, you may often see visualizations composed by a bar chart or a line chart, or a graph overlaid on the map. These kinds of data visualizations can be described as composite visualization. It is a design strategy that combines multiple views to form a coherent and meaningful layout. It can achieve a balance between strengths and weaknesses of each single visualization. This concept has been widely applied in the field of visualization. And these researchers have summarized 5 patterns of composite visualization, which we illustrate here. In these 5 patterns, view A and B are combined based on their spatial relations. Specifically, a juxtaposed view consists of 2 subviews that are composed side by side. And integrated views share the similar composition, but provide explicit visual connections, like lines connecting the corresponding data element between the 2 views. We can also superimpose views, which are formed by overlaying one view on top of the other, like the graph on the map example we showed earlier. And the fourth one overloads the views. It has one host view A and a client view B. B is embedded in the visual representation of A. And finally, 2 views can also be nested, with client view B being part of the visual representation of the host view A. A common example of the host view is a graph or a network. Both overloaded view and the nested views feature a host-client structure with 2 views sharing the same data encoding space. Recently, researchers began to create visualizations in immersive environments. They leverage the affordance of 3-dimensional space and embodied interactions in VR to simplify the visualization creation process. Such benefits also bring more possibility of composition among visualizations compared to the 2D screens. However, based on existing methods, building such composite viz is hard in immersive environment because currently, composite visualizations are usually created by experts ahead of time, and then they let consumers to experience them on devices. Many prior works focus on the support to asynchronous authoring. For example, they provide several toolkits to help developers create immersive visualization in Unity on web, and they let users look at it later. Some others also provide some real-time interactive methods, which encourage users to actively create visualizations using voice or hand gestures, promoting smooth user experience and agency. However, all those works just focus on creating single views or only axis-based views. These are relatively simple and they do not consider the composite visualizations in more general forms. In this work, we propose the user-driven creation of composite visualization. We argue that developers should provide users with active participation in the creation process so that they can manipulate and experience composite visualization with more freedom. To realize this, we consider how non-experts combine two things in their daily life. So each single view is considered as a combinable physical entity. Users can grab them and put them together. Conversely, they can also break a composite VIS into two single views. We listed three aspects when users compose two views. First, we need to consider the underlying data relations as it determines how those views are connected. The second important aspect is the type of composite visualization created by users. And finally, this requires our accurate interpretations of user intention conveyed by interactions. Yeah, a set of proper and reasonable mappings between these aspects is currently missing. To construct mappings, we first listed all possible ways of composition given the relations between two tables. It helps make decisions for some edge cases, like juxtaposed views are the only option for two mutually exclusive data tables. But we still need other determinants to differentiate the user intentions. Then we further propose a schema of creating composite visualizations with both the data relations and user interactions. And the kind of composite visualization is created by the embodied interaction. The target of interactions can be the whole view, the visual elements that represent the data, and the non-data elements, like the axis. And for manipulation, it could be single target or multiple targets. You can change the position, rotation, scale, or the motion of a single view in 3D environments. For two views, you can also collide them and separate them to show user intention of composing and decomposing views. During this process, we track the view relational state before and after interaction, such as the relative distance, scale, position between two views, and to determine which kind of composite views are created. To demonstrate the design space, we implement 5 representative cases, one for each patterns of composite visualization. Let's see demos. So this is the data for population density in United States. We create superimposed views of a bar chart and a map. The user can grab the whole bar chart as a target and collide it vertically on the map. When they release the bar chart, each bar will fly into the corresponding state. And the user can also decompose the view by quickly grasping the bar away from the map. Next is the compact data of players in Taekwondo. We create nested views with a stacked bar chart and a graph. Each player is a node in the graph, and edge represent the matches between them. User can extract a stacked bar and then put it into the node. So each stacked bar will transition itself to its corresponding node, and user can check each player's information by simply touching that node. To decompose, user can just grab a node and quickly drag it. Our third case is creating integrated views with nutritional data of cereals. To show visual data relations between two charts, user can put them close to each other with similar relative scales, and lines will automatically show up, connecting the related data properties in one-to-one mapping. User can also create visual links between multiple charts by adjusting their relative distances. With the same dataset, we can also create overloaded views with parallel coordinate plot. Users spread apart two axes with both hands, and a corresponding scatter plot will appear. Then user places that scatter plot into the areas between two axes, and the point in the scatter plot will automatically matches the corresponding line segments. User can also revert it back by bringing two axes closer. Finally, we present the creation of juxtaposed views with the same serial dataset. user can extend the two axes of the scatter plot with both hands simultaneously. They can reposition the view, they can resize the view as they want. They can also bend the view to a preferred curve, like the monitor surrounding you. And they can also check the data in different scales in this unlimited 3D space. With these cases, we conducted a user study with both expert and non-expert in visualizations to evaluate the usability and experience of interactions. We use Quest 3 with controllers to ensure the stability of operations. We set up the study environment with 4 steps and invited 16 participants in total. We encourage them to think out aloud when experiencing the interactions. The results show that most participants perceived our interactions as easy to use and effective. They thought the interactions were straightforward and reasonable. Here are some interesting findings. So first, participants prefer the direct manipulation of visualizations with a sense of physical affordance because this is very familiar to them. Second, they reported the active and embodied participation in the creation of CompositingVis as the potential of promoting understanding of data and view relations. Finally, they highlighted the flexibility of interactive method as it allowed them to quickly validate their ideas as well as present or educate with composite visualizations. And for more details, please check out our paper. Thank you.
Great, and thank you for the presentation. So we already received one question. So how do you deal with combinations at various levels of detail? For example, a bar chart could be used for the whole country and also for distinct within.
So as we mentioned before in the design space, there could be a lot of combinations of or compositions of visualizations depending on their data relations and the user intentions. So basically, if users combine two views, with both hands or vertically or horizontally, then can convey some different user intentions. So that's how we deal with combinations with various levels of detail. There are some automated stuff based on the the data relations, but our primary determinant would be the interactions.
All right, so I have another question. So you mentioned that you will consider users' intention, and this is very important when you design these kind of interaction techniques. So my question is, how do you recognize users' intention? When you
so
design?
basically, because we only consider two targets or two visualizations at a time, so there would be their relative distances. If they are close enough, then maybe it's a sign of composition. If the users want to stretch things or stretch the visualizations, it could be a sign of decompositions. So, but depending on the position they hold, it can be resizing, of course. So basically, we will focus on those very nuanced points to figure out what might be the intentions user trying to do or trying to realize by the interactions.
All right. So thank you for the answers. Due to the time limitation, we need to move to the next presentation. You can check the questions from Discord. There are many interesting questions and answer questions there. Right.
Okay, thank you.
Okay. So next presentation will be this is the table I want, an interactive data transformation on desktop and in virtual reality. And someone will give us the presentation.
Yep, I'm going to share the slides. Can everyone see the presenter mode?
So now it is the presenter mode. You need to switch to the presentation.
Oh, okay. Let me try it again. Maybe now?
It's great. Okay.
It's great. Okay, so I'll get started. So, hello everyone, I'm Sungwon, a senior PhD student from Virginia Tech, and today I want to talk about embodied data transformation where user can edit the data without writing any codes, but by doing gesture interaction within this immersive environment. So I first wanted to introduce the motivation, like how can we came up with this concept of embodied data transformation. We first found out that data analysts spend an excessive amount of time on data transformation to write some codes and to look up the library to find the proper codes, and furthermore, to use these tools, we also need to have expert coding knowledge. So to address such limitations, it seems like UI-based tools like Tableau has been proposed, where analysts can perform data transformation by simply clicking several buttons, or by doing several gesture interactions. So there's a many exploration already has been done, and they're saying that performing data transformation with this gesture interaction was much more effective and intuitive. And based on their successful exploration, it has been extended into the immersive environment. And they found that performing such gesture interaction within this immersive environment were even more effective and intuitive, because such interaction in immersive environment naturally involve our natural body movement. And also by having this intuitiveness, it improves sense-making process, which is frequently asked when we're doing data science tasks. And furthermore, by having this larger display space, enable us to interact with a larger number of data at the same time. However, we found that most of these immersive analytic techniques are focusing on visualization process. However, data science is not just about visualizing the data. We also need to edit the data. This is why we consider embodied data transformation is really needed. Imagine we are working on a data science tasks without embodied data transformation. After analyzing visualization, we may need to go back to data transformation process. To do this, we need to take off the headset, sit down on the desktop, and edit the data. Then we need to go back to the immersive space by wearing the headset again to analyze the visualization in an immersive space, which we think is very repetitive and cumbersome process. So once again, we found that embodied data transformation is really needed so that analysts can working within this single environment without changing their workspace, and also can perform data transformation without writing any codes or by having expert coding knowledge. So I want to share what kind of design process that I went through on building this prototype of embodied data transformation. Please first select several operations that are frequently used in the data transformation process, like extract, merge, filter, sort, and so on. So after we select several operations, then we design gesture interaction of our selected operations. We focus to design such gestures to best reflect our behavior in the real-world scenarios. For example, if we want to delete the data table, we need to grab the data table and throw it away, like how we throw the garbage into a trash can. So likewise, all the selected operations were designed within this intuitive manner. So from now on, I want to show how this embodied data transformation looks like in our prototype. So this is a demo video, and we first display all the data table in a semicircular layout so the analysts have the same distance to all the data tables. Okay, so we were going to show the extract operation first. To extract several specific columns, we need to select specific columns and think like we are grabbing out of the original data table, like grab it and pull it out. And here's another extract operations, grab it and pull it out. And we are about to merge these two data tables to merge all the columns in both data table into the one single data table by grabbing it and crush it together. Then the selected column, all the columns in both data table will going to be displayed in one single data table, and we have an option of displaying the use data table behind this. And here is another extract, and we're going to do another merge, but this time we're going to throw out delete the use data table. But same for merge, grab it and merge it together. And as I mentioned before, if we wanted to delete the data table, we need to grab it and throw it away. And we can also perform a sort operation by clicking it and drag it down or drag it up to sort the column in ascending or descending order. And we can also filter the column by clicking the bar chart on the specific columns. And we can also group or ungroup the sort by putting our both hands to squeeze it to group and expand it to ungroup. So likewise, all the interaction within this prototype can be done by doing just gesture interaction without writing any codes. So to systematically evaluate the effectiveness of our embodied data transformation, we have conducted a user study. And the user study was conducted to answer our research question like, can VI's spatial and embodied nature enhance data transformation tasks? So we collected 20 participants from university, and they all had experience in the data science. And comparison study. We had 4 testing conditions to effectively evaluate the impacts of computing environments, desktop versus VR, and interaction methods, WIMP versus gestures. So within these desktop settings, they need to working with the desktop and using the typical mouse interactions. But in VR, we need to use our body movement like walking around the space, doing some gesture interactions. And WIMP conditions, they need to click to interact with menu button interfaces to perform data transformation. But within gesture conditions, they were also used gesture interactions. And then we asked exploratory tasks for each testing conditions. There are one big data table on the top of their data other data tables. This was what we called target data table, which participants need to do by sorting, merging, extracting, like using all given operations to come up with the same format as the target data table has. So with those user study, we were able to answer our research question like, is gesture-based data transformation beneficial in VR? And the answer we found out was yes. Because we found that VR helped participants to build better strategies. For example, in VR conditions, we observed participants were trying to think more rather than trying all operations to come up with the answers, which resulted in fewer number of operations they performed to reach out to the answer. And next, we also found that VR improved provenance. I mean, like, they tended to keep more data tables that they already used, which resulted in fewer number of data leading the data table and having more data table on their workspace. We found that this is partially due to the larger display space provided in VR. As shown in the image, they display all the used data table behind their main workspace, so that they could go back to their previous stage or process at any time they want. While in desktop, there were no such enough space to display all those used data table on their existing workspace, which asking them keep deleting the data tables. And also navigating back to their previous stage in VR was a lot easier because they could just use their natural body movement like rotating their body or head. So we also found that VR had a similar time performance as desktop. Typically, interaction using body movement in VR is shown to be slower. However, such finding was not really evident in our results. We believe this is partially because our tested task was asking them to think a lot more. And as we discussed previously, we believe VR promoted strategic thinking, which also can be referred like it shortened the time needed to reach out to the answer. So we think that even though physical body movement takes a longer completion time to perform operations, it was resulted in similar time performance as desktop. So we believe embodied data transformation introduced a new paradigm for data science tasks, not only enabling in a fully immersive workflow, but also performing those without writing any codes. So I think from now, you guys can ask me, feel free to ask any questions. And I left a LinkedIn QR code if you want to ask further questions. And I'm actually looking for a full-time job next year, so feel free to reach out to me at any time you want. Thank you.
All right, thank you. So, we also received some questions. So first, I want to ask you that, virtual reality is 3D development, and your study focuses on data transformation tasks, which actually based on 2D. Okay, so how do you come up with this idea that you want to bring these tasks into immersive development? Why do you want to do that?
Because doing data transformation, we first focused on we don't really want to write some codes. We want to lower the entry barriers. And so to do that, we need to use a low code approach. And we found that gesture interaction is a lot more intuitive than doing on the desktop settings. That's why we are thinking that building data transformation within immersive environment that includes our natural body movement makes more sense to do the data transformation without writing any codes. I think that could be the answer of the motivation of this project.
Okay. So also, we received a question, do users have obvious performance differences or preferences associated with their VR experiences shown in the user study?
So are you asking me like, is there any like distinct differences between desktop and VR settings?
The performance differences or
Performance difference.
preference
I think, yeah.
experience.
So the big differences that we found has a similar time performance, but I think this can be also interpreted as not big differences. But what we found that as is VR really promoted strategic thinking in VR. I mean, in the data science tasks. So it really shortened the time required, even though the VR includes a lot of body movement. So I think this could be the big differences between the desktop and VR.
Okay. Well, so a follow-up question is that do you think that, for example, you notice that the VR showed the potential to provide improved provenance over desktop, right?
Yeah.
So that's because of the VR environment, or do you think it is the impact of the gesture detection?
I think that is the impact of the VR. Since we have this larger display space, we have more space to keep our data table at any place that we want. While in the desktop settings, we are working on like a limited screen, which we don't really have space to display all the use data table when data analysis gets more complex. So I would say that's the reason why we have in VR.
Okay, yeah, great.
Yeah.
Thank you very much for the answers. So
Yeah.
you will also need to answer questions in Discord. Okay.
All right. Thank you very much.
Yeah, thank you. Let's switch to the next speaker. So which the title of the presentation is VoxAR, Adaptive Visualization of Volume Rendered Objects in Optical See-Through Augmented Reality. And Matthew will give us the presentation.
Hi, my name is Matthew Castellana. I'm with Stony Brook University. Today I'll be presenting VoxAR, Adaptive Visualization of Volume Rendered Objects in Optical See-Through Augmented Reality. To begin, let's provide a little background context. For augmented reality technologies, there are two key types, optical see-through and video see-through. In optical see-through, you see the real world presented through a lens, while virtual images are added by projecting light into your eye. In video see-through, a camera captures the real world and a screen displays it to you, with virtual images drawn over the captured image. In this presentation, we'll focus on optical see-through, specifically using the Microsoft HoloLens 2. This method has the advantage of letting you see the real world without any barriers, but it also has some drawbacks. For example, it's challenging to create fully opaque graphics since we're adding light to light. Additionally, reproducing colors like black can be difficult, if not impossible, because of the way we generate virtual images, again, using additive light. Now let's discuss visualization techniques. In AR, a key visualization technique for displaying scientific data is volume rendering, which helps explore and interpret volumetric data. This is usually done with transfer functions that map the data's intrinsic values to a range of optical properties like color and opacity. Now let's take the case of an augmenting a volume rendered scientific data set onto a real world scene. Let's say a doctor wants to visualize medical data in the operating room. What kind of challenges might arise? First, there's the issue of placement. Where in the scene should the object be placed? There could be a number of metrics for this. For now, let's just say it determined that this area on the wall is a good place. If we render the skull as is at that location, it's possible for the pixels of the rendered virtual content to be inaccurately perceived, which is another challenge in scientific visualization. Methods have been created to enhance the visibility and color accuracy of virtual objects in optical see-through head-mounted displays, but these techniques often focus on each goal separately. This can lead to inconsistencies in the relationship between color values across the spectrum. These challenges inspired us to create VoxAR, a method for augmenting volume-rendered objects in optical see-through head-mounted displays. VoxAR adapts to real-world surroundings and adjusts transfer function colors to better visualize scientific data. it uses a twofold approach. First, it determines an optimal position for displaying a virtual object in the user's field of view based on user-defined preferences. And second, it adjusts the colors of the transfer function to distinguish the rendered volume from the background. Let's take a look at each of these steps in a bit more detail. We start by using the RGBD camera on the HoloLens to identify potential placement locations within the scene. For each pixel, it provides a 3D location along with data for assessing collisions and occlusion, helping us find candidate surfaces for placement. For AR objects that aren't surface magnetized, we create synthetic depth images from the original RGBD data, testing positions from determined by rays through each pixel that end at a specific distance from the camera. These positions are then evaluated in parallel on the GPU using Unity compute shaders according to constraints such as these. These objectives are attached to AR objects in Unity and can be customized and weighted depending on their importance and user preferences. Once the location images are evaluated, VoxAR outputs rankings of each location for each objective, which can then be combined and the optimal location determined. Users can run this placement once, or if desired, run it continually, moving the object when its current placement falls below a certain score threshold. Now, I'd like to go into a bit more detail about one constraint as it ties in with the second half of the pipeline: color discernibility. As we state here, it maximizes the perceptual difference between transfer function colors and colors in the real-world scene. But what does that mean exactly? Well, let's take a look at this example scene, where we want to place an AR volume that uses this transfer function. Ideally, the volume should show up well against the background, and the information should be understandable. Given that, how do we evaluate each location? Well, to evaluate color, we first need to understand how it's measured, which is done using the color space. On the right is the C chromaticity diagram showing the full visible spectrum of light in the large horseshoe shape, and each boundary represents a different color space, each serving a specific purpose. The most common is the RGB color space visualized on the left, which represents colors based on the amount of red, green, and blue. However, there's another color space called CLAB, which measures lightness, or white versus black, red versus green, and yellow versus blue. Now, the advantage of CLAB is that the distance between colors reflects perceptual differences for a user. For example, colors 1 unit to the left or 1 unit to the right of a specific color are perceived as equally different from the original. Now, returning to our color discernibility constraint, by projecting our image and transfer function in CLAB, we can identify which image pixels are close to the curve, indicating that they are perceptually similar to the transfer function, and which are not. You'll notice an intersection here. This patch corresponds to the yellow area on the wall. While this wall is a great empty area for placing an AR object by other metrics, this intersection of colors says otherwise. Here, this image shows that pixels with colors near the transfer function are closer to red, which means bad, while those farther away are closer to green, which means good. We use this metric to evaluate the image according to our color discernibility constraint. So now that we've discussed object placement, let's look at the second half of the pipeline, the transfer function adjustment. To prevent background colors from interfering with a holographic image of the rendered object, we formulate a constrained optimization approach for adjusting the transfer function. This approach aims to ensure that, first, the colors in the adjusted transfer function are clearly distinguishable from the background, and second, the color control points in the adjusted function maintain visual characteristics similar to those in the original transfer function. So here we have the initial transfer function in RGB color space. We then project it into CLAB color space, and we're ready to begin the optimization process. We have 4 key constraints that we have formulated for the transfer function adjustment optimization problem. The constraints determine a penalty cost for each adjusted transfer function candidate, which the solver attempts to minimize to obtain a final result. The first is the background discernibility constraint, which attempts to move the transfer function to minimize its interference with the background pixels. The second involves maintaining perceptual characteristics so that the differences between the colors within the transfer function perceptually look the same. We do this with perceptual color difference, LAB congruency, and hue separation. The third prioritizes colors remaining close to their original color tone. And the fourth ensures that all transfer function colors from the larger CLAB color space have a valid correspondence in the smaller RGB color space. These constraints are then solved using covariant matrix adaptation evolution strategy, an optimization algorithm. It iteratively creates a population of candidate solutions, evaluates them, selects the best ones, and then creates new candidates through mutation and recombination. And here are the results. You can see that the VoxAR recoloring shows up much better against the yellow wall for this placement. Another example, the VoxAR recoloring is much more distinguishable while maintaining perceptual similarity of the original transfer function. Here we have a video example. And here's a comparison with the state of the art. Both improve visibility against the background. However, VoxAR maintains transfer function color consistency. Here's another example of an original transfer function versus a VoxAR recoloring. And you can notice that it recolors it away from red due to the couch. Here we have an example, and here we have an example of the placement component continuously finding new locations when the current location scores below a threshold. Now, to evaluate our system, we conducted a user study in which users had to count primitives hidden inside a volume, as well as primitives of a specific intensity level. We compared the effects of manual user placement versus automated VoxAR placement. As
2 minutes left.
2 minutes. As well as the original versus the recolored transfer function. The results indicate that users perform better under our system with regards to accuracy and completion time. Here's an illustration as to why. Users found it harder to see the cube inside the blue circle with the original transfer function, and in the white circle, users mistakenly thought there was a cube in the original transfer function when in reality it was actually a hole. Overall, the results show that VoxAR's transfer function recoloring improves data perception. Thank you.
Great, thank you, Matthew. This is great work. I really appreciate such fundamental research on user perception in immersive environment. Well, because of the time, we only have one question. So, so when you designed your transfer function, do you consider the data distribution or the alpha encoding? And so basically, if the scenario or background is very complex with many colors, do you think it will work well?
Currently, it sounds like you're talking about a complex background. Currently, it doesn't take into effect the complexity of the background. For example, if you have a simple background versus a textured background, it sort of does that by proxy in the sense of it considers a range of pixels around the location. So if there are poor colors in that area, it'll take that into account, but it doesn't take into account texture or frequency. We're considering that for future work.
Okay, great. Thank you.
Yep.
Okay, let's move to the next presentation, which will be selection. So the title is Precise Embodied Data Selection in Room Scale Visualizations while retaining view context. So Shaozhang Dai will give us the presentation.
Just sorry. Just share my screen first. Is the share screen okay?
Yeah, great.
Right, cool. Okay, hello everyone. My name is Shaozhang Dai. I'm a PhD candidate at Monash University in Melbourne, Australia. And I will be presenting our work on precise embodied data selection with haptic feedback while retaining room scale visualization context. Immersive environments enhance data visualization and analysis in many aspects through the use of 3D space. Unlike traditional click interactions, effective interaction are essential when exploring in 3D environments, where selection and manipulation present unique challenges, especially for large-scale visualizations. Distance 3D target selection techniques, such as recasting and extendable hand, has been widely studied but still facing challenges like imposition, especially for occluded targets. Alternatives like content zooming or teleportation might, however, disrupt the context. The through-portal interaction, on the other hand, allows a consistent level of accuracy for object manipulation at various distance and still provide a user a clear overall context. However, existing research on portal interactions has barely addressed how to optimally position the portal initially. Additionally, studies on how the through-portal interaction can enhance immersive data analytics is notably lacking. Therefore, we propose a novel combination of extendable hand interaction and the through-portal interaction. We'll call it Magic Portal. Our approach provides intuitive portal placement and allows process interaction with distance objects over a large 3D space. Here is a quick demo. So for our Magic Portal interaction, we have come up with a two-phase interaction method. First, hand extension to reach close to the desired location, and then process interactions through the portals. To enter the hand extension phase, the user makes a phase pose, and the reach can be extended by adaptive gain function. They can stretch their physical hand to move the virtual hand close to the position for further interactions. An exit portal is attached to the virtual hand, where the entrance portal is fixed on the left side of the user's point of view. When the user opens their hand, the exit portal becomes fixed into the chosen location, and the entrance portal is then relocated in front of the user. In the interaction phase, the user can peek through the portal to get a closer look. And then they are allowed to put their hand through the portal for further interactions. The portal metaphor also allows us to shrink the range of actual workspace to a relatively small range in front of the user, which allows us to overlap such range with the range of a robot arm for encountered haptic feedback. In this case, we use a desktop robot arm to place a tangible proxy for the user to touch in the physical space when the user is actually interacting with the data point in the virtual space. However, the extension phase still requires some mid-air aiming and stretching, which could be very fatiguing. Hence, we have also prepared a fatigue measure to better understand the change of fatigue during the interaction. We use some vacuum cameras and tracking markers to record the arm movement for performance evaluation and fatigue analysis. We also use subjective fatigue measurement VoxAR 10 and our newly developed NICER model to evaluate the change of fatigue. We have designed 2 comparison studies, and each study involves 12 participants. We're creating a room-scale 3D scatter plot, and it's approximately 10 meters times 10 meters times 8 meters in size, and the participants were standing at least 5 meters away from the nearest point. Participants are asked to approach and interact with 30 highlighted points, and the completion time and hand movement will be recorded for further analysis. Every after 6 targets, they will have a short break and report their current fatigue score. Our first user study is a comparison between extendable hand interaction, like the traditional go-go interaction, and our Magic Portal interaction. We have found strong evidence that Magic Portal interaction outperforms the extendable hand in terms of trajectory length, number of attempts, but found no evidence of a difference in completion time. The fatigue result also suggests that Magic Portal interaction is less fatiguing. And the post-study feedback shows more participants prefer the Magic Portal interaction. Our second user study is a comparison between the Magic Portal interaction with and without haptic feedback. However, in the result, we cannot find obvious evidence that happy portal or normal portal has better performance. The post-study survey, on the other hand, shows that more participants prefer to use the interaction with haptic feedback due to better immersive experience. We also propose 3 potential use cases for magic portal interactions in immersive visualization. The first use case is multi-target selection with haptic feedback, which provides haptic feedback for every data point in the workspace. The second use case is portal scaling, which allows different portal sizes for different functions. For example, an upscaling portal can be used for group selection, where a downscaling portal can be used for focus on specific data points. The last use case is a 3D geospatial visualization. The extendable hand allows user to navigate through the buildings easily, where the portal enables flexible viewing angle. There are several limitations in our current study, and first one is recruitment challenges. To accurately record participants' arm movement, we require them to wear tight-fitting clothing, which might not be comfortable for everyone, and lead to a gender bias towards the male participants. In the current study, the portal's orientation is fixed, limiting users' viewing angle. In the future, we plan to develop an intuitive rotation control as well for better navigation. Due to the hardware constraints, the study is conducted exclusively for right-handed users, and we plan to develop the interaction so that the user can choose which hand they want to use for engagement. We hope this work can inspire more novel and effective interaction methods in immersive environments. Thank you for your attention.
Great. Thank you for the presentation. So we have some questions. We did a user study before, and we compared hand size visualization and table size visualization, and also room size. Okay, as we noticed that room size visualization for point cloud data is not very easy for the users to notice those points, the locations, or the structure of the point cloud clusters. So
Yeah.
why do you choose the room scale visualization?
Oh, that's exactly why we want to do the study in the first place. Because as you said, room scale visualization is very it's not ideal maybe at this point for people to try, especially for scatter plots. But that's because, in our opinion, one of the major reasons is it's very hard to select, especially to select a distance target. And especially another issue could cause in a room scale visualization is the occlusion is happened very often. Like you can't say what's behind what you can say, and many of the points actually blocked. That's why we want to have a selection with decent targets, not only for selection but also for navigation. Because we can, with our magic portal, you can see through the occluded targets, and then you can say which target you want to interact first through the occlusion, and then you can interact for the interactions.
Mhm. Okay, so another question is that what is the main purpose of interacting with remote data instance while maintaining the current position? I mean, I think the person who asked this question is that since it is an immersive environment, 3D environment, you can go there, right? So why do you do this remote interaction?
Yeah, like we can actually use other techniques to interact with remote objects like teleportation, or we just rescaling the whole visualization to a really small size in our range of touch. But the point is, when we're doing that, we're actually changing our context of the whole visualization. And we want to keep it because sometimes we want to jump from point A to point B, which is in a room scale visualization can be very far away from each other. So we believe by keeping the context of the whole visualization, if you want to navigate through a large range in a room scale visualization, it will be much easier for you to do that.
Okay. So do you notice when in the user study, and do you notice that the user it will be difficult for them to judge the depth of many instances, like points?
Yeah, exactly. So in our first user study, we are comparing between the portal interaction and the example hand interaction. So in the hand interaction, the user cannot see through the portal like they have a magic lens. So they have to judge the distance by themselves. Some people with very good perception with depth, they can do that with no problem, but some people cannot do that. That's one of the reasons we believe the portal interaction is better, because it actually gives you a closer look of the targets that is far, so helps you to navigate and select your target.
Great. Okay, thank you very much.
Thank you.
To the next presentation then. And so next presentation will be preliminary guidelines for combining data integration and visual data analysis. And Adam will give us the presentation.
Great. Thank you for the introduction. Good morning, everybody. Oh, there we go. Hold on. We're going to go back to the beginning of the slides because we don't want to present the end of them. Yes.
Adam,
Cheers. Here we go.
Okay, great.
Can you hear me?
Yes.
Great. All right. Like I said, good morning, everybody. My name is Adam Kasha. I'm a fifth-year PhD student at Georgia Tech. And along with my co-authors, Ashley, Remco, and Alex, I'm excited to present to you preliminary guidelines for combining data integration and visual data analysis. Oh my gosh, I apologize. All right, here we go. There we go. So a while back, I was watching some analysts merge columns from separate data sources into a single file to visualize in Excel, which is a pretty standard visualization task, I'd say. However, they spent a lot of time on data integration. Tasks like copying, pasting columns, cleaning missing data. They spent much less time actually visualizing the data. And so I thought to myself, what if we combined the process of data integration with visual analytics? Would that speed things up? Keep analysts more on task? Would anything be lost by combining these things? So what might this look like? Well, this could look something like having menus for encoding attributes in your visualization that can also integrate attributes from other files automatically into your current data set. So in other words, instead of thinking about the integration challenges, you might be thinking more about visualizing the data instead. And so we synthesized two questions about how to support data integration during visual analytics. First, where and how should data integration operations be supported in tandem with visual analytics operations? And second, how will incorporating data integration into an ongoing visual analytics process affect users' behaviors? And so our aim in this paper is to contribute preliminary guidelines for incorporating data integration into an active visual analytics process. So to answer these questions, we developed two interface alternatives featuring contrasting approaches to the data preparation and analysis workflow. A separated interface featuring manual file-based ex situ integration, that is a separate step from visual analytics over in Excel. And we developed a combined interface, which featured automatic UI-based in situ integration that is merged with visual analytics operations like encoding and filtering. And so with these interfaces, 16 study participants were asked to complete a practice task and 2 live tasks with each interface. The tasks were to browse for patterns, generate insights, and summarize relationships between attributes distributed across multiple CSV files. And so afterwards, participants would then debrief by comparing their thoughts, processes, and insights while using each interface. So let's get to the results. First, we analyzed the time that participants spent integrating by comparing stacked horizontal bar charts, where the height of the bar is the minutes that participants spent integrating in the dark pink versus analyzing data in the light gray. So to simplify the results, we're showing just one pair of charts for just one of the 4 tasks from our conditions. And by comparing the time spent integrating, which are the dark pink bars, between the separated and combined interfaces, we found participants exhibited several unique integration strategies. So many participants would integrate all their attributes up front or in a few intervals throughout the session in both interfaces. So this was expected, as this is that classic workflow that tools like Tableau support. Some participants exhibited a unique strategy. They exclusively visualized data on the fly on purpose using in situ integration, spending little to no time explicitly integrating data. We then computed bootstrapped confidence intervals of the total task time and percentage of time spent integrating that was between the interfaces. So by comparing these times with the time spent integrating, a surprising pattern emerged. See, interface and task type did not significantly affect total task time, but those with the combined interface were spending much less time integrating data and more time encoding and visualizing it. We then compared this with total interactions and found a similar number of interactions between the interfaces, further suggesting that participants may have been uniquely allocating their time differently between the interfaces, potentially spending more time analyzing data in the combined interface. We also observed users' analytical behaviors related to satisficing and exhibiting bias from a sense-making perspective. So for satisficing, many participants felt tension between time and accuracy, even though we allowed unlimited time to analyze the data. So while many felt in situ integration simplified analysis, it may affect the balance of sense-making that proceeds under time constraints and data overload. For bias, we observed examples of confirmation bias and anchoring effects, particularly when participants would integrate first and then analyze their data. Importantly, these biases persisted even when our interface afforded integration with a single menu click. And we believe that this mirrors that common expectation of mentally separating data integration and analysis, like P9 points out here. So with our results, we synthesized 3 guidelines for designing future visual analytics interfaces that can support integrating attributes throughout an active analysis process. 1, show where and how data are being integrated. 2, use in situ integration for exploring the space of attributes. And 3, balance manual and automated approaches. So providing transparency in data integration is vital. Participants often trusted anonymous integration, where potential join errors are hidden by the interface. Yet outcomes from such integration could be dangerous if not carefully evaluated. And systems like Cashman et al.'s Kava system solve this by showing a pop-up which explains the join process before the final integration. However, some participants still felt tension between exploring all the attributes and satisficing on just a few. Systems like that automatically select relevant attributes could alleviate pressures, either by offering more attributes on demand or suggesting related attributes using semantic similarity. So while in situ integration can help users spend more time on data analysis, issues from ex situ integration still persisted, such as missing potentially relevant attributes. In our combined interface, we saw that visual sense, like showing the file names, offered users immediate feedback on their integration and promoted more data-driven decisions during integration. Differences in users' behaviors between ex situ and in situ integration revealed preferences for each approach. So manual integration aided participants in recalling relevant attributes and understanding the data better. So to ease the ex situ integration pressures, we should provide on-the-fly data preparation when integration is critical for sense-making. Alternatively, when that integration is trivial, designers should aim for a minimal but fluid design for automated in situ integration to support the user's concurrent mental processes while maintaining that data context. So for example, Tableau's data blending, I think, does this really, really well. The data blending technique automatically joins secondary attributes from other data sources into a primary table that you're visualizing, which maintains human-in-the-loop control over the data while simplifying the integration process. And this allows users to explore attributes faster and focus more on visualizing the data. So overall, our guidelines aim to help designers more seamlessly incorporate data integration into visual analytics. Integration should be visible and tailored to user workflows with visual cues for aiding sense-making. And both manual and automated methods like Tableau's data blending should be preferred at different stages of analysis. So how do these guidelines relate to the open questions we raised in the beginning? Well, first, in terms of supporting both integration and analysis operations, participants integrated data in several unique ways during analysis with no significant time difference between the interfaces. Thus, in situ integration may allow for faster exploration of attributes compared to ex situ methods, freeing up more time for analysis. Second, in terms of effects on user behavior, participants used integration to generate hypotheses and insights while also revealing patterns of satisficing and cognitive biases. So future visual analytics tools should ensure transparency throughout data integration while balancing both automated and manual methods. And finally, we identified several opportunities for future work that build off the limitations of our study, including types of integration, task requirements, and users' experience. So while this study focused only on column concatenation and selection, issues like deduplication and data quality still remain underexplored. And so one way we could study these could be single table data wrangling, which would offer more complex integration tasks and conditions that we can compare alongside UI-based field calculation. Task performance effects were also inconclusive. It's unclear if there's a threshold for changes in user behaviors based on task, dataset, or type of integration. And finally, it's unclear if combining data integration and visual analytics depends on familiarity with software, analysis practices, or the domain of the data. So for example, decision makers may not change their existing routines even if on-the-fly integration is possible. At the same time, our results suggest starting with a single file of attributes may be neither preferable nor realistic. So to read more about our work, you can find the paper Data Analysis and Code at the QR code above. Thanks for listening.
Thank you very much for the presentation. And because of time limitation, we only have one question. So you identified 4 distinct data integration strategies used by the participants.
Yes.
And so could you elaborate on how these strategies might influence the design of future visual analytics tools?
Absolutely, yes. So we have, and here's just a chart of all the different the data here. So I think the design here shows that you should prefer the types of support that you give in your tool for integration, whether you require users to do manual integration versus allowing them to just automatically integrate a data attribute on the fly at different stages in the analysis. I think because we see that users prefer to either put all their attributes together up front before they analyze, or they like to analyze attributes kind of in chunks as they go. These differences in how people tend to think about their analysis typically lend better support to either manual integration, which makes them more confident in their data, or automatic integration, which helps them speed up their process a lot faster. So there's different times at which you should prefer to do which approach.
Okay, thank you, Adam. There was another question I just received, because it's also related to another talk in our session, so I think it's interesting to discuss this. Earlier, we saw a talk on data transformation. So do you think your result can apply to data transformation instead of data integration?
That's an interesting question. I'm not sure if people think the same way about transformation as they do integration. I think we really tried to control for the idea that you don't know where your data is coming from in this study. And I think with transformation, it's interesting because it's the same data, but I guess in a way, yeah, it's now different from what you expected it to be, right? So I think it could probably be something where you don't see the transformation process. That could probably be a similar overlap in this work, where when people didn't see the work, it was hidden and it was anonymous. There was a lot of issues with people coming up with spurious correlations and analysis. So that's probably the one thing I think would be interesting to explore, is whether it's hidden versus shown to the user. Probably very similar to what we saw from the effects here of anonymous integration. Yeah.
Okay, thank you very much. All right.
Of course, thank you.
Thank you. Let's move to the last presentation. So the presentation is illustrating model steering interactions from users via data and visual design props. So Anna will give the presentation.
Thanks very much. So I'm presenting this work on behalf of my colleagues, Maddie Shang and Eric Broshu, who I worked with at Tableau Research. And the goal of this study and this research was to do kind of a few things, addressing the issue that it's actually inherently hard to design for human AI interaction. And I'm not the first person saying there's a lot of really interesting literature in the Chi community about this very specific problem. And so what we try to do here to understand and address some of this is to propose the idea of using data and design probes as a way to understand early in the process how users actually want to interact and provide feedback to machine learning models. What I'll show you today is how we reify these ideas in a co-design study with participants, and from this distill a design space or identify some interactions and encodings related to human AI interaction. And we sort of summarize these as future forward challenges for semantic interactions as human AI interaction becomes more complex in the future. So a lot of the motivation for this work was that a lot of the existing literature, interactive machine learning, is focused on developing a prototype, proposing some new interaction and encoding, and then actually testing it with users. But one of the tensions that we found and that motivated us was that machine learning models inherently limit what people can do, but so do the visual design choices that we made. And so we actually wanted to go really earlier in the process of saying, well, if you didn't have a lot of these restrictions, what would you want to do? What kind of feedback would you want to give a model, and how crazy could it get? And so our research is situated a little bit earlier in the process, looking at probes and sort of more generative idea spaces for eliciting these kinds of interactions and these ideas from users. And if you haven't seen this really interesting paper from Sanders et al. That is a really thoughtful description between like probes, toolkits, and prototypes, I totally recommend it. And this is their diagram that I'm borrowing here. So one of the things we wanted to do was really try to get a solid and reasonable understanding of users' preferences before we committed to any kind of code. And we have two instruments that we propose to use this, a data probe and a visual design probe. Both of the goals of these probes are to encourage creativity and divergent thinking about the ways that we want to explore and interact with AI and ML systems in data analysis processes. But they're also trying to control this a little bit. So with the data probes, we're actually trying to control for different characteristics of data sets that participants might bring. So familiarity or just specific characteristics. And we also wanted to be able to use a common baseline. We also introduced specific errors and flaws in the data probe to see how people would react to it, which is not something that we could necessarily guarantee with data that they're bringing in from the wild. The goal of the visualization design probes was also to reduce potential attribution errors. So understand, is something working well because the interaction is working well or because of the way that it's designed or something else? So we really wanted to isolate the specific effects of the encodings and the interaction choices. So the way that I think about this is if we think of our lab studies or the way that we think about testing our prototypes as kind of being more like out in the real world, this is more like a lab study, where we're testing it with mice and simpler systems to kind of get at some of these more fundamental characteristics. So the data probe that we used here was a movies data set. Part of the reason that we chose it was because we thought it'd be familiar with a lot of people, so it would be a common baseline. All of that actually proved to be kind of interesting as well. We used a small number of examples, and we introduced deliberate errors in the data set. So we had the original data set as well as the outputs of some model that we would then visualize. We had 4 different visualizations that we used to test how people wanted to interact. So we started with basic visualizations that people were familiar with, like bar charts and scatter charts, and then we added some embellishments to them as well, with the different encoding choices. We also included a table, which may or may not be controversial, and this is because most of our participants who were engaged in some form of data analysis but had varying expertise, ranging from a machine learning engineer to a data analyst, all routinely used tables and Excel to do their analysis. So the table was our baseline, and then we looked on to visual probes using some very common visual encodings. With each of these, there was some inherent interactions that they could do, right? So for the table, they could overwrite things in the table. For the bar chart, they could move things around or add color and probability. For a scatter chart, they could do similar interactions and so on. It was a limitation of our study that we did decide what these interactions were rather than totally letting people go completely carte blanche. So we added some sort of a grounding to them. But as you'll see in a video in a few moments, because of the environment that we used to conduct our study, people could get pretty creative and change this stuff up quite a bit. So we ran an elicitation study. We got initial background information from folks. We set up the instruments, which is the data and the design probe, and we gave people some examples of how to use our system and interact with it. And then we had kind of a Wizard of Oz style co-design space where a person would actually manipulate the visual encodings, tell us what they wanted to do, and then we had somebody in the background that did their best to try to emulate some of those interactions in near real time if possible. So I want to show you what some of our participants did.
Here, a participant is not only making minor changes, but fully changing the bar chart encoding to make it easier for them to provide feedback. This example, a participant creates a new cluster of movies that are more representative to them. Here, a participant changes aspects of the table to make things stand out more, and adds another column to indicate when they agree with the machine learning model results. Finally, this participant represents multiple genres of movies as well as linkages between the different movies they are interested in.
So we aggregated all of these results across people with different expertise. We got a design space of all the different kinds of interactions that people wanted to engage in for manipulating what seemed like a fairly simple data set. And they were also able, because of the environment that we used, to introduce a lot of different ways of interacting with the individual marks to convey some information to the model, which could be, I want to change the label of this movie, or I want to introduce a new cluster, I want to merge these clusters. Some of these have been seen before in some prior research, especially for taking a look at things like topic modeling. What was interesting was when participants particularly wanted to interact with the probability, which changed our goal from a classification task to a more complex task. And also when they started to introduce multiple labels or even date labels that would be sort of out of the training data set, which again shows how task complexity also grew as they had more freedom to interact and were able to do different kinds of interactions. So we were also asked participants throughout the study what they were actually trying to communicate and tell the machine learning model through these interactions. So one of the things that they wanted to do through interactions was add additional dimensions to the data. So for example, hey, I'm creating a new class here, and I want you to think about it. And it's different from the other classes that you might have. Maybe these are just movies that are nostalgic to me or that I care about, but I'm adding another column inherently. Another one was trying to prioritize the model's attention. So some people would take a look at something and say, oh, I agree with what the model is doing here, and I want it to ignore that, but I want it to pay more attention to this stuff that I'm interacting with here. And other things is that they actually wanted to use this as a way to communicate to other people and actually have the machine learning model be more like an assistant to help them in that process. So folks with lesser machine learning backgrounds would say, oh, I want to do something, I want the support of the agent, I want to check it out, and then I want to communicate back to the model designer or the data scientist. They also told us why they were hesitating to interact. And this was important about a probe relative to a prototype, where we really want people to use our system. We let people, we let people know when they didn't have to interact. So reasons they didn't interact was because they were concerned about introducing bias, because they felt there were too many degrees of freedom and it was overwhelming, or because the encoding didn't naturally support interaction. They also let us know about the cadency and the frequency of updates, whether they wanted the AI agent to decide for them, whether they wanted to perform a series of tasks and then actually tell the agent, hey, update the result, or whether they wanted more of a speculative execution kind of framing, where they could see what the AI agent was doing and then decide whether they wanted to act on that decision or whether they wanted to continue to do some interactions and give more information to the model. So in conclusion, perhaps as a provocation, sometimes leading by prototyping can be considered harmful, especially in a complex design space like human-AI interaction, where the designer actually makes a lot of decisions on behalf of the study participants. People also want to do things that AI and ML models might not be able to handle, like change a classification task to a more complex task than the one that the model was originally trained on or prepared to do. And we also found that people don't necessarily want to interact with too many points when providing model feedback. And so this actually means that the machine learning model has to work with a very limited number of points. So the next step is really thinking about new feedback paradigms for visualization-mediated human and AI interaction. And if that little diagram I have below is interesting to you, please feel free to reach out and chat with me about it. So thanks very much. And with that, I am happy to take any questions.
Okay, thank you, Anna. And so we have only one question. So when in the illustration study, how do you talk to your participants? How do you like motivate them to discuss these new ideas?
Yeah, everybody had different baseline levels of motivation. And there's a different way that you can sort of prepare your script ahead of time to prepare participants so that you have some sort of control, even in the way that you are consistently interacting. So what I usually tend to do when I prepare these kinds of studies is I have a script ahead of time. And for every participant, they all hear the same sort of spiel from me to, say like, do you want to do this or do that? So it's consistent. They're all hearing the same thing. And then I also have a pre-specified set of prompts with timings that I sort of bring up to people like, oh, it's been 2 or 3 minutes of no activity. So let me now chat with you and prompt you in a specific way. So some participants don't need that. They engage a lot and very organically, and others are a little bit more hesitant. So long as you have consistency in the way that you communicate with each one, you can kind of control for your own influence in the process. So the participant actually elicited this, not necessarily because you made them do it through like, go ahead, do something. So that's usually how I handle it.
Great, Anna. And we don't have more time, so you can read the questions from Discord and answer from there. All right. Thank you all for the presentations and also for your great work. And thank you everybody for joining us today. Okay, so let's close our session today. Okay. Bye-bye. I think we're done. Thank you very much. Well, in the end, we don't have so much time anymore.
Oh God, my internet completely died 10 minutes before my talk. I had to run around the building to find a connection. Anyway, thank you. Bye.
Yeah, bye-bye.